Now bear with me for just a second here. I want to make sure you can see everything. Alright, this is Euclid Book 3. Please, let's try this again. This is Euclid Book 10, proposition number 54. Yeah, we're way past 3 now. Okay. If an area be contained by a rational straight line and the first binomial, the side of the area is the irrational straight line, which is called binomial. For let the area AC be contained by the rational straight line AB and the first binomial AD. Okay, hold on. What is the area of AC? It's this area plus this plus this plus this. This whole thing is AC. Okay, this is a rational straight line right across here. And this is a binomial right here. This line is a binomial. Okay. I say that the side of the area AC, well, what is the side of the area AC? Well, the side of the area AC is this right here, okay, is the irrational straight line, which is called binomial. For since AD is a first binomial straight line, we're now saying that this is a first binomial straight line. Let it be divided into its terms at E. Okay, now, keep in mind that E does not bisect AD. Okay? Now, AE is going to be greater than ED. Okay? This length right here is greater than this length right here. It is manifest that AE and ED are rational straight lines commensurable in square only. What does that mean? Okay. This is a rational straight line. This is a rational straight line. But they're only commensurable in squares. So what does that mean? We're going to have to make squares. We're going to take the length of AE, we're going to make a square out of it, and that's going to be this one. We're going to take the length of ED, we're going to make a square out of that one, and it's going to be this one. Okay? So these two square areas are commensurable, but these two lines are not. Okay, the square on AE is bigger than the square on ED by a square on a straight line commensurable with AE. Now AE, this line right here, is commensurable with AB. Alright, and that's by Euclid Book 10, definition number 2, 1. Okay. Let ED be bisected at point F. Okay, so this is going to bisect ED. So now EF and EF and FD are the same length. Then, since the square on AE is greater than the square on ED, by the square on a straight line commensurable with AE, which happens to be AB, okay, because we made a square out of this too. Oh yeah, we made a square out of this. They took this length, and all four sides of this square are the length of AB. Therefore, if there be applied to the greater AE a parallelogram equal to the fourth part of the square on the less, that is the square on EF, okay, so if we apply to AE a parallelogram, okay, which is going to have the same area as this right here, and deficient by a square figure, it divides it into commensurable parts. And this is by Euclid Book 10, proposition number 17. Let then the rectangle AGGE. Well, where is the rectangle AGGE? Okay. What we're going to do is we're going to have to draw it. So, two sides of that rectangle is going to be the length of AG, and two sides of that rectangle is going to be the length of GE. Okay, so now we're going to draw this rectangle. There you go. AGGE, there's your rectangle. Okay, now the area inside of this one right here, is equal to the area inside of EF. And we're going to apply this onto AE. Therefore, AG is commensurable in length with EG. This is commensurable with this. Sorry. Scratch that. This length right here, and probably what it'll be... Okay, so we want this to be GE. Okay. All right. Okay. Let's try this again. This length right here is commensurable in length with this length right here. So in other words, this is commensurable with this. Let GH, so we're going to draw this one right here. EK, we're going to draw this one right here. FL, we're going to draw this one right here. Be drawn from GE and F parallel to either of the straight lines AB or CD. Okay, so these lines here are parallel to this. Okay, and let the square SN, this is a square SN right here, and it's going to be constructed equal to the parallelogram AH. Well, so in other words, the area inside of here is going to be the same as the area inside of here. And the square NQ, this area right here, is going to be equal to GK. So the area inside of here is going to be the same as the area inside of this. This is by Euclid Book 2, proposition number 14. And let them be placed so that MN is in a straight line with NO. Okay? So this line is in a straight line with this. Therefore, RN, this line right here, is in a straight line with NP. Okay? And let the parallelogram SQ be completed. Well, the parallelogram SQ is this plus this plus this plus this. All four areas combined make the area of SQ. Therefore, SQ is a square. And this is by the lemma we just gave in the last proof. Now, since the rectangle AGGE, that's this one right here, is equal to the square on EF, so where is EF? Right there. So this area is equal to this area. Therefore, as AG is to EF, okay, so as AG is to EF, so is EF to EG. So as alright, as this is to this, so as this is to this. That's by Euclid Book 6, proposition number 17. Therefore, also as AH, this area right here, is to EL, this area right here, so is EL, this area right here, to KG, which is this area right here. So as this is to this, so as this is to that. We're talking about areas here. As this area is to this area, so as this area is to this one. This is by Euclid Book 6, proposition number 1. Therefore, EL is a mean proportional. This is a mean proportional right here between AH and GK. Okay. This is a mean proportional between this and this. But AH is equal to SN. This is the same area as this. And GK to NQ. This and this are the same areas. Therefore, EL, okay, EL is this, right here, is a mean proportional between SN and NQ. This is a mean proportional between this and this. But MR, well, where's MR? Well, MR is right here. Is also a mean proportional between SN and NQ, between this and this. And that's by the lemma we gave in the last proof. So EL is equal to MR. This is equal to this. So that it is also equal to PO. This is equal to this, and this is equal to this, and this is equal to that. We're talking about areas here now. But AH and GK, GK, are also equal to SN and NQ. So if we add this and this together, we'll get the same amount of area as if we were to add this and this together. Therefore, the whole AC, this whole area right across here, is equal to the whole SQ. Okay, so this area right here and this area right here are exactly the same size. That is to the square on MO. Okay. So now we're going to take the length of MO and we're going to draw a square out of it. Alright. So MO is a side of AC. Okay. So this length right here and apparently this length right here are the same side, are the same size. Now we're going to say that MO is a binomial. For since AG is commensurable with GE, as this line is commensurable with this line, therefore AE is also commensurable with each of the straight lines AG and GE. Okay, so AE is commensurable with AG, and AE is commensurable with GE. And this is by Euclid Book 10, proposition number 15. But AE is also by hypothesis commensurable with AB. So this is commensurable with this. Therefore, AG and GE, these two lines here, okay, both of these lines are commensurable with AB. This is by Euclid Book 10, proposition number 12. And AB is a rational line. Therefore, each of the straight lines AG and GE, this line here and this line here, they're both rational. Therefore, each of the rectangles AH and GK are rational. This is a rational rectangle. This is a rational rectangle. This is by Euclid Book 10, proposition number 19. And AH is commensurable with GK. These are commensurable areas. But AH is equal to SN. This area is equal to this area right here. And GK is equal to NQ. This is equal to that. These two areas are equal. Therefore, SN and NQ, these two areas right here, that is the squares on MN and NO. Okay, so if we were to take the line MN and make a square out of it, and we were to take the line of NO and make a square out of it, then the area of this square and the area of this square would be the same area as this and this. And they are these areas that I just told you about, this the square on MN and the square on NO, those two areas combined are both rational and commensurable. And since AE is incommensurable with the length of ED, we know that this line here is incommensurable with this line right here. While AE is commensurable with AG, this line is commensurable in length with this. And ED is commensurable with EF. ED is commensurable with EF. Therefore, AG is incommensurable with EF. These two lines are not commensurable. And this is by Euclid Book 10, proposition number 13. So that AH is also incommensurable with EL. Okay. This area here is not commensurable with this area right here. This is by Euclid Book 6, proposition number 1, and Euclid Book 10, proposition number 11. I'm sorry, Euclid Book 6 proposition number 1 and Euclid Book 10 proposition number 2. I was wrong again. But AH is equal to SN. Okay? This is the same area as this. And EL to MR. This area is the same area as MR. This is the same area as this. Therefore, this area is not commensurable with this one. But as SN is to MR, as this is to this, so is PN to NR. Okay, so as this length is to this length. Okay, and this is by Euclid Book 6 proposition number 1. Therefore, PN, right here, is incommensurable with NR. And this is by Euclid Book 10 proposition number 11. But PN is equal to MN. And that may be Euclid Book 10 proposition number 2, I'm not really sure. But anyway, maybe 11, I don't know. But PN is equal to MN. This length right here and this length right here are exactly the same. And NR to NO. This length is equal to this length. Therefore, MN is incommensurable with NO. These two lengths are not commensurable. And the square on MN is commensurable with the square on NO. Okay. So, if you were to make a square out of this length and a square out of this length, those two squares would be commensurable. These two lines are also rational. Therefore, MN and NO, these two lines right here, are commensurable and square. They are rational. Therefore, MO, right here, is a binomial by Euclid Book 10 proposition number 36 and the side of AC. So this length right here is the same as this length right here. Alright, I will tell you more in a future video. Stay tuned.